Assalamualaikum. We are continuing today with part 2 of chapter 14 or module 5, processor structure and function. Previously in part 1, we have looked at processor and register organization. In part 2, we are going to look deeply inside the instruction cycle. An instruction cycle includes these following stages: fetch, execute, interrupt. You may recall this from part 1 slides. We are now in a position to elaborate more on the instruction cycle. First, we must introduce one additional stage known as indirect cycle, which I will explain further in the next slide. Students know that the execution of an instruction may involve one or more operands in memory, each of which requires a memory address. For example, we can have instruction mul total. We can also have two operands at AX total. And don't forget, we also have indirect addressing. So for example, move BX, comma, total. Yeah, indirect addressing. If indirect addressing is used, then additional memory accesses are required. So we have students are familiar with fetch instruction, execute, and interrupt. So now we are talking about indirect, where you can think of the fetching of indirect addresses as one more instruction stages. So now we have 4, including indirect cycle. And from this diagram, yeah, you look at the arrow, we can have a few cycles actually. The main activities, yeah, consists of alternating instruction fetch and execution. So it's very simple. You fetch, then you go to execution, and then a simple one, and you just get the next instruction. Fetch, execute, fetch, execute. And the second kind is when we have indirect. Yeah, so after an instruction is fetched, after you have fetched the instruction, you examine to determine if any indirect addressing is involved. If so, you move to indirect cycle, yeah. And then the required operands are fetched, all right. And then we execute. After we execute, we go back to, oops, wrong lane, you fetch and go again. The third one is using interrupt, right? So after you have fetch, you execute, yeah, and then you found out that an interrupt may need to be processed. So you go to interrupt, yeah, before you fetch the next instruction. So fetch, execute, interrupt. And lastly, yeah, of course, yeah, you can use all 4 cycles, yeah, sorry, 4 stages. So from fetch, you found out you need indirect addressing, and then you solve indirect addressing, you got the data, and then you execute. After you have execute, you found out, yeah, there is some interrupt, you solve the interrupt, then you can cycle again with fetch. So these are the 4 kinds of fetch that you can do, with execute, with interrupt, and also with indirect. Another way to view this process is shown in this slide. This illustrates more correctly the nature of the instruction cycle. So once the instruction is fetched, its operand specifiers must be identified. Each input operand in memory is then fetched, and the process may require indirect addressing. Remember, register-based operand need not be fetched. Once the opcode is executed, a similar process may be needed to store the result in main memory. Now we are going to look in detail, all the 4 cycles in data flow: fetch, indirect, execute, and interrupt. We start with the fetch cycle. Before that, students need to understand that the exact sequence of events during an instruction cycle depends on the design of the processor. We can, however, indicate in general terms what must happen. Let us assume that a processor employs these registers: PC, program counter, instruction register, IR, memory address register, MAR, and also memory buffer register, MBR. I would like also to introduce a new term, RTL, which is right to left, as shown here. So from right, so what we read is the PC will go into MAR, right, from right to left. And also, this T1, T2, and T3 is the timing sequence. At T3, MBR, content of MBR will go into instruction register. During the fetch cycle, an instruction is read from the memory. The slide shows the flow of data during this cycle. So we start with PC, so look at PC. The PC contains the address of the next instruction to be fetched, which is address 100. This address is moved to the memory address register, MAR, and placed on the address bus. So that 100 is transferred to memory. Meanwhile, control unit requests a memory read using the control bus. We are going to go to the next 2 micro instructions. So in T2, we're going to do these 2 instructions. So first, what we have in memory, is the instruction. So at 100, the instruction is move AX total. So it will be sent into data bus and put inside MBR. So that is T2. At the same time, PC needs to be incremented by 1. So now PC becomes 101. Lastly, at T3, we start with MBR here. The data in MBR is moved into instruction register, IR. The opcode of the instruction will be decoded and translated to determine the microoperation for that particular instruction. Once the fetch cycle is over, the control unit examines the contents of the IR to determine if it contains an operand specifier using indirect addressing. If so, an indirect cycle is performed. So now we are looking at the second data flow, which is indirect cycle. And this is the RTL steps. Indirect cycle involve fetching data from memory before we can initiate the execute cycle. So we have example, add AX, total in parentheses. I would like to remind students that the parentheses is actually in the textbook means indirect addressing. And let's assume total is at address 2400 in memory. So inside the IR, they will see that the address part, the second operand is actually an address to another address. So that's why we are going to go into indirect cycle. So we look into the address part of the instruction register, and we found out that it is not the actual address of the operand, but a pointer to another address. So 2400, which is the address of total, is sent into memory address register. This content is placed on address bus. Next, control unit will request memory read. And inside memory, we found out that at address 2400, inside it is another address 3F00. This address is actually the address of the operand that we want. So we put it on data bus and send to MBR. Now the MBR has the actual operand and will be put together with the address part in the instruction register. The fetch and indirect cycle are simple and predictable. However, the execute cycle takes many forms. The form depends on which of the various machine instructions is in the instruction register IR. This cycle may involve transferring data among registers, read or write from memory or I/O, and the invocation of the ALU. These two are example of instruction execution. So we have add AX BX. Yeah, so control unit will generate signal to ALU because it needs to do addition. We also have jump next. So CU will have to want to transfer the address, yeah, to fetch the next instruction because we have the jump instruction. So let's test our knowledge, yeah, to see if we actually understand the slides before this. Look at the example. This is the characteristic of a hypothetical machine. We have the instruction format, yeah, with 4 bits of opcode, and then what is the address? 8 bits. We have the integer format, sign and magnitude, and then we have the registers. We have 2 familiar one, PC and IR, but we don't have AEX, BX, and so on. What we have is an accumulator. We call it AC. And then for these opcodes, yeah, the 4 bits, we have a list, and yeah, so if the opcode is 001, it means the instruction is load accumulator for memory. Yeah, so we have 3 opcodes listed here. Okay, so first let me introduce a few things. Yeah, so we have our memory, and there are 2 segments from 300 to 302. Yeah, this is the instruction segment. Yeah, this is the instruction segment, and then from 940 to 941, that is the data segment. And we also have the content of our registers. Yeah, so the current program counter has address 300, and the instruction register. Yeah, so PC has the address, IR has the instruction, and the instruction right now, what is in 300? 1940, and nothing inside accumulator yet. So we decode 1940. We found out that 1 is the opcode, and that is load, yeah, opcode load. And what are we loading? We are loading what is inside address 940, the data inside address 940. And go to step 2, and that is 0003. So we put 003 inside accumulator. Now we have the content of accumulator. At the same time, remember, we need to increase, add PC from 300 plus 1, now it becomes 301. Yeah, so from 301, we go and find 301 is 5941, and we put it inside our instruction register, the instruction, yeah, and we decode the instruction. It means add, yeah, into whatever is inside 941 to add into accumulator and save it inside accumulator. That is the instruction 5941. So in step 4, it shows the execution. Yeah. So in 941 is 2. We add to the original AC 3, right? And we add, and the amount is 5. We put it inside accumulator. At the same time, please increase PC plus 1. Now it becomes 302. And in step 5, 302, the instruction inside 302 is 2941. Put it inside IR. And opcode 2 means store. We want to store the content of our accumulator inside address 941. And step 6 showed that. So 005, we store it inside 941. Yeah. So this is how execution cycle works. After you have fetched, you have found out what is the operand address, where is the instruction address. So you execute one by one. Yeah, you decode and get the address and do the execution. If add, you add. If load, you load, and so on. So the first part, yeah, here, these step 1, step 3, and step 5 is actually fetch and decode. All right, and the execution is done on the right. Step 2, step 4, and step 6. These are the step-by-step explanation of the previous slides, which you can look at one by one in the PDF slide format. We move on to example 2 to show you an indirect cycle. The instruction is increment num in a bracket. So stalling interpret bracket as contains of. So bracket num in a bracket represents indirect addressing. And increment, the opcode is 01000, which is in hexadecimal, it is 4. First, we are going to fetch, yeah, and in fetch instruction, we decode it, and then we see that there is an indirect addressing, so we need to go into indirect cycle, and then we execute. At the beginning of the fetch cycle, the address of the next instruction to be executed is in the program counter PC. In this case, the address is 100. The first step is to move that 100 address to memory address register, MER. Then the second step is to bring in the instruction. The 100 address in the MER is placed on the address bus, and then the control unit issues a read command on the control bus, and that result will appear on the data bus. And what is it? The actual instruction itself, increment num indirect address. And this will be copied into the memory buffer register, MBR. Don't forget, at this time, we also need to increment the PC, but we're not going to show that in this animation. And lastly, the third step is to move the content of the MBR to the instruction register, IR. Because the instruction specifies an indirect address, therefore, we must go into indirect cycle after this in the next slide. So once an instruction is fetched, yeah, so the next step is to fetch source operand. But because the source operand is indirect address, so there's another subcycle, indirect addressing. So the address field of the instruction, yeah, which is num, is transferred to MER, which is 450. This is then used to fetch the address of the operand. So 450 go into address bus, and then we look in the memory, and we see that 450 is not the actual operand, but it points to another address with 560. And that address 560 will be put on the data bus and sent into MBR, which will replace the old one. And finally, the address field of the IR is updated from the MBR, so that it now contains a direct rather than indirect addressing. It now contains 560 instead of 450 in a bracket. We are still in example 2. We are going to have a closer look using RTL symbol in a table to show you indirect cycle. First, at T0, PC has 100. That is the address of the current instruction that we want to fetch. Fetch cycle starts at T1. So what happened is, what's inside PC, the content will be moved to MAR. So MAR now has 100. At T2, 2 micro operations will be executed. First, we go to the memory and look what is inside address 100, and the content of that address is 4450. This is a one address instruction. So 4 is the opcode, which is increment, and 450 is the address. So we take that 450, and put it inside MBR. From memory, it is inside MBR. At the same time, PC is incremented by 1. Now it becomes 101. And lastly, what is inside MBR is moved to IR. Now IR has 4450. That concludes our fetch cycle. If 450 is a direct address, then we can go to execute cycle. However, in this example, we are using indirect address. That means we have to do indirect cycle. So let's move on to indirect cycle. What happens in indirect cycle? So at T1 for indirect cycle, this is T1 indirect cycle, but T4 for the whole cycle. So the address field of that instruction, so this 450, the address field, is transferred into MAR. So that's why MAR only has 450. You cannot bring the whole 4450 because the 4 of the front is opcode and that is instruction. MAR is memory address register. It can only contain address. So now address 450 is in there. At T2 of indirect cycle, so we go to the memory, we go to address 450, and we see what is the content. And that content is 560, and that will be put inside MBR. And finally, at T3, we will update content of MBR, which is the address, and we will update it inside our IR instruction register. So now our instruction register has 4560. So that concludes the whole thing. After this, we will go to execute cycle. Now it's students' turn to try example 3. The instruction is store and indirect cycle. Store, the opcode is the hexa number is 2, and the address, indirect address for N is 103. As well as this example 4. Please determine first whether it has indirect cycle or not. After we have looked at fetch cycle, indirect cycle, and execute cycle, now we are going to look into the fourth data flow, which is interrupt cycle. So all computers will provide a way to interrupt the fetch, decode, execute cycle. Yeah, because sometimes a user wants to read, write, print, and sometimes the computer hangs and we want to do Control C, Control Z, or critical errors occur. So interrupts can be caused by hardware and also software. Interrupt processing involves another step to fetch, decode, execute. Because if there's an interrupt, we need to pause our current execution and go to interrupt handler. Like the fetch and indirect cycles, the interrupt cycle is kind of simple and predictable, like shown in this slide, figure 14.8. The current content of the PC must be saved so that the processor can resume normal activity after the interrupt. So if there's an interrupt, whatever we're doing, we have to save the address of that. So the content of the PC are transferred to the MBR to be written into memory. So from PC we go to MBR. The special memory location reserved for this purpose is loaded into the MAR from the control unit. It might, for example, be a stack pointer. So if you want to run the interrupt, we got the address from control unit into MAR. The PC is loaded with the address of the interrupt routine. As a result, the next instruction cycle will begin by fetching the appropriate instruction. I'm going to show you an example of interrupt. So we have CPU and I/O, and CPU will run the program. So we start with an active segment 1. Then there's a write request. So of course we need to pass the data to input-output. After the write is done, we give it back to CPU, and CPU will run segment 2. In the middle of segment 2, interrupt request comes in. So we pause segment 2 and sends it to interrupt handler to execute the interrupt. When interrupt is done, it is sent back to CPU, and CPU will continue until the end. So this is the end of 14.3. We have looked at processor organization and register organization in part 1. And in part 2, we looked at 14.3, instruction cycle. So after this, we will move on to pipelining.